Hello grade 12s. This one, a revision of grade 11 integration part 2. So just following on the first video on that grade 11 integration. So the next concept that we need to talk about is something that Mr. Rees-Messer did with you. I know he did this with you properly. And these are called Riemann sums. Now, Riemann sums is another way to find the area underneath a curve. And this is why Riemann sums connect to the definite integral that we discussed previously. But Riemann sums is almost like the first principles way of finding the area underneath a curve, of finding that definite integral. And again, I just want to reiterate, please remember the definite integral can be equal to the area underneath a curve, but isn't necessarily equal to the area underneath a curve. Riemann sums specifically finds you the area underneath a curve. Okay. Now on your formula sheet, it tells you that the area, according to Riemann sums, is the limit of n tending towards infinity of b minus a over n, and then sigma I running from 1 to n of the x of f of xi. Now, if you recall from last year, each one of these has like a little meaning. This, right there, is going to be the width of the rectangles, because we normally go with Riemann sums and we split the area underneath a curve into rectangles, and this is the width of one of those rectangles. Now this over here is the height of the rectangles. We did refer to this a little bit earlier, that f of xi, which is then going to be my y value, is then the height of the rectangles. Now I will go and I will sum all of these heights, and I will multiply it by the width. And the reason I can do that simply is because, yes, if I'm working out the area underneath a curve and I divide it up into rectangles, it's width times height, plus width times height, plus width times height, plus width times height. But because all the widths are exactly the same, we take it out as a common factor and we put it over there. So this is just summing the areas of the rectangles underneath the curve. Now if I leave off the limit right over there, then what I find over here is an approximation of the area underneath the curve. Because if I leave off the limit, they will tell me, for instance, find the area underneath the curve using 10 rectangles. So my n value will become a known value. I will divide up into 10 rectangles, so n is equal to 10, which means I then don't need the limit of n tending towards infinity. And then what I end up getting is an approximation of the area underneath the curve. Whereas the moment n tends towards infinity, I'm using an infinite number of rectangles underneath the curve, which means that becomes the exact area underneath the curve. So last year you did examples of an approximation of the area underneath the curve, and you also did examples of the exact area. Now the good news is in grade 12, in the final exam, they don't really do these formal Riemann sums where you have to do all of the substitution and stuff like that. You just need to go and you need to understand the following. If I, for instance, go and I say, I want to take this area underneath this curve and I want to split it up, let's hope I'm going to get this right. I want to split it up into, let's make it 6 rectangles. So there's 1, 2, 3, 4, 5, and then 6 rectangles. So each time I use the upper limit over there. So that means this one, and I just want to color it in with a slightly less dark color. So I've got this rectangle plus this rectangle. If I add up all of these rectangles, and they are supposed to have equal widths. I know this one looks like it's slightly thicker, but these are supposed to have equal widths. Okay. So then if I go and I add up the area of these rectangles, I will get an approximation of the area underneath the curve, because my n here is equal to 6. It's not getting infinitely big. But what you also need to realize is you need to realize if I then go, instead of having 6 rectangles, I end up having 100 rectangles, then these widths become smaller and smaller and smaller, which means these little fat rectangles become thinner and thinner and thinner, and there's lots more of them, and it becomes more and more accurate. Now, when I use this Riemann sum way of finding the area underneath a curve, there's going to be what we call an error in my measurement. So I'm going to make an error on the area underneath the curve because I didn't get the exact area, because I didn't go and make n infinitely big. Meaning if n is infinitely big, lots of rectangles which means the width is lot thinner. I can actually redraw just to give you an idea of what that looks like. So if I have like 1,000 of those rectangles, then the rectangles will look like this. So the rectangles will almost be as thin as one of these lines, which means it becomes much more accurate. So there's obviously then going to be a percentage error in the measurement. And this is what they asked in the IB 2019 paper. So in the IB 2019 paper, they went and they said in question 11, Robin is using rectangles to estimate the shaded area. So the shaded area is the exact area. But obviously these rectangles, if I add them together, you'll see I'm getting way more of an area than I'm supposed to get. Now they ask, calculate a percentage error to 1 decimal place. So if I want to calculate the percentage error, I first need to go and I need to work out the exact area, and I also need to go and work out the area of these rectangles. So the exact area is actually very easy to do. We've spoken about that, saying the exact area is going to be the integral going from 1 to 5, starting at 1, ending at 5, of that function, so x squared plus 1 dx. And I can just calculate this on my calculator. Because the nice thing is, the nice thing is they've given me all the information I need. They've given me the function. So that integral of x squared plus 1 going from 1 to 5 is then equal to 136 over 3 units squared, because I'm working the area. And again, because that all of those areas were above the curve, I didn't have to go and use the absolute value brackets in there. So this is the accurate area using the definite integral. But now I have to almost like use a Riemann sum. Now, they did say that they're not going to do Riemann sums anymore in the final exam, but they're going to use this version of just working out the area of the rectangles. So you could have gone and you could have said the approximate area is equal to, and you could have just gone and done them manually, one by one by one. So instead of using the Riemann sum formula, I would just go and say the width every single time is 1, 1, 1, 1. So I'm going to take that 1 out as a common factor, because technically speaking, you don't actually need it. But you'll see just now this makes it slightly easier. Then I have to go and I have to work out the heights of each one of these rectangles. I need to work out the height at 2, at 3, at 4, and at 5 of that function. So this is why I'm just going to use my table function, and I'm going to type in that x squared plus 1, and I'm going to say I want it to start at 2, get me the height, the f value at 2, and then end all the way to 5, and step in once, because my width is 1. So this one has a height of 5, this one has a height of 10, this one has a height of 17, and this one has a height of 26. So I can then just go and I can say add these. So this is going to be 15 plus 17 plus 26. So that means my approximate area is 58 units squared. Good. Now I still need to answer the question, what is my percentage error? So my percentage error is going to be the difference between the actual area and this one divided by the actual area. Got it? Now you need to understand that my percentage error in this case has got to be positive, because I worked out a much bigger area than I was supposed to work out. So my percentage error is then equal to that 58 minus 136 over 3 divided by what it should have been, the 136 over 3. So let's just do that. So I've got 58 minus 136 over 3 divided by 136 over 3. And that gives me 27.94%. You could multiply it by 100 if you want, just to get the percentage. But it's an error of 27.94% on this particular question. So that's pretty much the only stuff I really needed to discuss with you. So yes, it ended up being a slightly shorter lesson. Thank you for listening.